Hello and welcome to College Physics 1, Lecture 25, Rotational Dynamics and Moment of Inertia. So up until this point, we've been introducing all these different rotational quantities, that being rotational quantities of position, velocity, and acceleration. So we were looking at angular position, angular velocity, angular acceleration. And then in the last lecture, we looked at the angular equivalent of force, which is torque. What we're really doing here is slowly building toward making a Newton's second law equation for rotation. So instead of F equals ma, something else. And we're actually pretty close to being able to do that. At this point, we have developed enough equations to write an equation for torque based on angular acceleration. The equation here is given: torque tau is equal to the angular acceleration alpha times mr squared. Again, there is a direct correlation between force and torque. Torque is the rotational equivalent. So remember, just like force is a push or a pull, torque is a twist or a turn. If you apply a force to an object, F, you cause that object to accelerate, F equals ma. Well, if you apply a torque to an object, you cause it to rotate. Same general idea. So to see where this equation that I've written comes from, let's take a look at our definition of torque from our previous lecture. Torque is given by Rf sine of phi. Now, in this case, we're going to be looking at the tangential component of this acceleration. So when we say sine of phi, we're going to be talking about a 90-degree angle in this case. So sine of 90 is just 1, so this is really just r times f for this example. So we have torque equals Rf, but we know from Newton's second law that force is ma. So really we have Rma. But from 2 lectures ago, we saw that tangential acceleration, a, is given by alpha times r. So this equation becomes r times m, and then times alpha r. So this is where that equation comes from. You can see here, if you just do a little rearranging, notice that there's 2 r's. This is alpha m r squared. So that's where this equation is coming from. I don't make my students derive equations in my basic physics class like this, but it's important to sometimes see where the equations come from. We have combined 3 equations: the equation for torque, Newton's second law, F equals ma, and then the comparison between angular acceleration and regular acceleration, namely a equals alpha r. Anyways, so we have an equation here, torque equals alpha mr squared. Now, in many situations, we're going to have a rigid object, a large object, with perhaps multiple forces acting on the object, each producing a torque. So we would have to find the net torque, the total torque acting on the object. Like you can see in the picture there on the right, there are 3 forces acting on the object, each of them causing a rotation, in other words, a torque. So if we were to try to solve for the net torque, we add them up, right? You add up each individual torque produced by those 3 individual forces. Well, using the equation above, each individual torque is given by alpha mr squared. So we write it out in full in this second equation, alpha m1 r1 squared plus alpha m2 r2 squared, and so on. But notice I'm not putting a subscript on my alphas. We don't need to put a subscript there because in this case, it's a rigid object. Every particle along this solid object on the right should be rotating at the same rate. So alpha is the same for all of them, the angular acceleration. If it wasn't, that means other parts of the object would be accelerating at different rates, which means they'd be moving further in a shorter amount of time. In other words, the object would be warping and or breaking as a result. So that is not the case. We don't need a subscript on the alpha, which means we can pull the alpha out. We can factor it out. So that leaves behind alpha times the sum of mr squared, like you can see right there. So this is a really important result. We have torque equals alpha times the sum of mr squared. So just for a moment, let us take a look at that right-hand side of the equation, namely the sum of mr squared. By definition, we're going to call the sum of mr squared the moment of inertia of the object. Now, we'll talk about the definition of it here in just a moment, but it's mass times the distance between the axis of rotation and the location of the mass, r squared. So be careful. I italicize this here for my students. I emphasize the importance of this. R is not necessarily a radius, okay? So be very careful. R is the distance of the mass from the axis of rotation. That is something that I try to drill into my students' heads because it is so important to remember that. And you'll get practice with that idea here in just a moment when we work on some examples together. Well, looking at this equation, we have mass, which is measured in kilograms, times a distance, which we measure in meters, quantity squared. So the units are kilogram meters squared. Okay, well, we haven't really said what moment of inertia is. I mean, okay, we're saying it's mr squared, but what does that really mean? Here's the weird but real definition of it. Moment of inertia is the rotational equivalent of mass. Now that sounds weird, right? That hardly seems to make sense because mass is just mass, right? I mean, it's how much stuff there is in something. But think about the actual physics definition of mass. I will say, when I was learning this material back in the day when I was a student, moment of inertia was one of those quantities that just never really made sense to me. And I don't know if it was just my lack of ability to grasp the concept at the time, or I can't remember if my instructor had described it well enough for me to really understand it. But think of the real definition of regular mass. By definition, mass is the resistance to acceleration. The more mass there is in an object, the harder it is to get that thing to accelerate. So with that in mind, we can make sense of what moment of inertia is. If mass is the tendency to resist acceleration, moment of inertia is the tendency to resist angular acceleration. And suddenly it starts to be a little bit more clear. The more moment of inertia an object has, the harder it is to get that thing to rotate. And notice in the equation, it is not exclusively based on mass, m. It's based on mass and your distance from the axis of rotation. So that is why the example on the right in the pictures is important. On the top image, you have students or kids or whatever on a merry-go-round, and they're sitting along the outside edge of that merry-go-round. As a result, it's actually fairly difficult to get that merry-go-round spinning. But if those same three kids move to the center, they still have the same mass, it's still the same merry-go-round, but if all they do is move to the center, it's suddenly easier to move the merry-go-round because their value of r got smaller. They got closer to the center of the rotational axis. And thus their moment of inertia decreased, meaning it's easier to accelerate the object. So the real definition is the rotational equivalent of mass, but I think this definition is so important. It's the tendency of an object to resist angular acceleration. With that in mind and comparing it to the real definition of mass, the tendency to resist regular acceleration, I believe that this quantity becomes more straightforward, or at least somewhat more digestible. So, we have a new equation, so let's apply it to an example. The example says, consider the situation shown. The rods in this picture, those white solid lines, are 10 centimeters long. It says, determine the moment of inertia. Oh, I just noticed a typo. I put moment of inertial. There's no L. Just moment of inertia. Ignore that. If the object is rotated A about axis A, which is this here. This is axis A. And B about axis B. The same three masses, but this time it's going to rotate around down here. So let's go ahead and try to work out this problem. We'll first look at part A, which is the top figure. We have this axis A, which is that white dashed line running top to bottom. And then three masses, M1, 2, and 3, connected by those white rods. Each is 10 centimeters long. So if we wanted to calculate the moment of inertia for that object, we know by definition it is the sum of mr squared. Where in this case, we have, three different masses, right? M1, M2, and M3, which means we are going to have three moment of inertia terms in our equation. So we'll write this as M1 R1 squared plus M2 R2 squared and M3 R3 squared. That is the full form of this equation for this particular setup. Three individual masses, so three terms in our equation. So as I described, the masses are already given. We know all those masses. So really all we have to worry about in solving a problem like this is making sure we understand what the distance r is for each of the three objects. So let's go ahead and see if we can work this out. Mass 1 is given in the picture as 1 kilogram. The distance r1, let's take a look at the picture. Remember our definition. The distance r is the distance of your mass from the axis of rotation. So basically you have to ask yourself, how far away is my mass from the axis? Well, this vertical dashed line is the axis. Mass m1 is on the axis. It's literally lying straight over it. So as a result, that distance is 0, right? R1 is 0. And so we can plug in 0 meters here. It is right on the axis of rotation, so there is no value r. Mass 2 is given to us as 1.5 kilograms. And if we look at the picture, mass 2, this guy over here, mass 2 is 10 centimeters away from the axis of rotation. So if that is the case, R2 is 10 centimeters. Now note we want to convert to base units, so that would be 0.1 meters. And don't forget to square that quantity. Okay, well, then we go to mass 3. Mass 3 is 1 kilogram. And we just have to take a look at the distance for this one. This one can be a little trickier. Some students will get a little confused often with figuring out the distance on this one. But if you notice, the axis of rotation, again, is that white vertical dashed line on the left side of the picture. And so if that is the case, then we need to figure out the distance of mass 3 from that axis. Well, right up here, we can see that this is also going to be 10 centimeters. It's still 0.1 meters. So with this in mind, we can plug in all our numbers and hopefully get the correct answer of 0.025 kilogram meter squared for part A. So again, the only thing we really have to do for these problems is figure out the distance of each of the masses from the axis of rotation. So this brings us then to part B. Always show your full work, so always write out the equation, as annoying as it can be, or redundant as it can sometimes be. You should always show full work. So M1 R1 squared again, M2 R2 squared, and M3 R3 squared. So in this one, we're now looking at the bottom right picture. It's the same three masses connected by the same rods. They're both 10 centimeters again. So it's the exact same set of masses. The only difference is how we're rotating it. So now what we're seeing is the rotational axis is straight into and out of the screen through mass 1. And it's rotating around mass 1 here. This is axis of rotation B. So, same exact process. We're given all the masses already. We just need to figure out how far away each one of these three masses is from that axis of rotation. So these equations set up in a very similar manner. Our mass 1 is still 1 kilogram. Now the distance r1, well, mass 1 here is again right on the axis of rotation. It's a different axis of rotation, but it's still passing through mass 1. So it is a distance 0 away from that axis. It is right on it. Mass 2 is the 1.5 kilograms. And its distance is again 10 centimeters. Mass 2 is 10 centimeters away, so 0.1 meter quantity squared. Okay, so this just brings us then to mass 3. Mass 3 is a kilogram, and its distance is a little bit harder to figure out because the distance of mass 3 is actually the hypotenuse of a triangle that is formed here. So if we look at this, we have this being R3. So we actually have to quickly calculate what R3 would be. So we'll do that kind of off on the side here. I'm actually kind of running out of space. Let me put the parenthesis in here. Yeah, I'm going to need that space. Okay, so let me just do this right along the side of the triangle. So R3, by Pythagorean theorem, will be the square root of 0.1. I'm going to write this kind of briefly, squared plus 0.1 squared. So that's the two sides of the triangle, 10 centimeters and 10 centimeters. So 0.1 meters squared plus 0.1 meters squared, you take the square root of that, and you get 0.141 meters. So R3 is 0.141 by the Pythagorean theorem. So this will give you an overall answer of 0.035 kilogram meters squared as the answer. So there you have it. So both parts of this were very similar. In fact, the only difference in our equations was the final distance, right? These two distances here were the only thing that changed at all in the equations. But that does mean we have a different answer. And so what that is showing us is that even though we have the same masses connected the same way, we changed how they rotate and thus saw different moments of inertia. So very important to see that, I believe. Okay, so what we've done is look at the moment of inertia for this random assemblage of masses, right? A bunch of random masses connected by rods, very, very random. There's no real reason this shape or whatever should exist. It's kind of uncommon. But there are common shapes that rotate as well. And it turns out that there is an actual equation for every single moment of inertia for every single common shape. So whether you have a cylinder rotating around, a sphere, a shell, a slab, a rod, whatever, each individual object has a different moment of inertia equation. So the equation that we've been using, the sum of mr squared, really only applies to random assemblages of masses or different particles along an object. But if you have a common shape that is rotating, you can reference this table to figure out the equation you need to solve. So this, for my students, this is a table that is given on a formula sheet for exams. I do not expect students to memorize equations, especially these ones, because, I mean, come on, good luck with that. This is a given bit of information. So this is a really handy reference to have when you're working on moment of inertia problems. We won't, of course, go through the derivations of where each of these comes from, but you could just kind of theoretically come up with one real quick. So perhaps this hoop, if you tried to analyze the moment of inertia is for a bunch of particles along this hollow sphere, or I'm sorry, this hollow cylinder. Well, if you did that, each one of them has, if you think of the sum of mr squared, each one of them has a mass. So we'll say mass 1 times a distance r away. But the distance of each of these particles is the same distance. They're all the same radius away. So you don't need a subscript on the r. So you'd have m1r plus m2r squared plus m3r squared, and so on and so on and so on. So what you really end up with is a bunch of masses summed together times the quantity r squared. Well, if you sum up a bunch of masses, we can just call that a total mass m, and there's your equation, mr squared, that we use for a cylindrical hoop. So, there is a way to derive these equations. I just kind of quickly showed you one of them just for the sake of, showing you where they can come from. But that gives you at least a rough idea. So reference this all the time if you need to. And be careful, dimensions are shown on the picture. So sometimes, here it's using the radius of the sphere. Here you're looking at using the entire length of the rod. So just be careful. It does reference the dimensions in the picture so that it helps you. Okay, well, at the very beginning of this lecture, I said that we've been trying to build Newton's second law for rotation. So let's go all the way back to the beginning of this lecture just for a moment. We have the equation here, torque is alpha mr squared. Well, remember, we said that torque is the rotational equivalent of force. Okay, well, alpha is the rotational equivalent of acceleration. Right? And here we have this mr squared term, which is the rotational equivalent of mass. So we actually have built our F equals ma equation. If you look at what we have torque, again, which is our rotational equivalent of force, equals moment of inertia, our rotational equivalent of mass, times the angular acceleration, which is the rotational equivalent of regular acceleration. So the rotational equivalent of Newton's second law is torque equals I alpha instead of F equals ma. Very, very important for going forward. And so we're going to look at a problem-solving strategy on how to solve problems that use this equation. And then we're going to do 2 examples together that actually use it. So here is your problem-solving strategy. Not every single problem will use every one of these steps, and not necessarily in perfect order either, but it at least does guide you a little bit as to what you need to be looking for in most of these problems in order to solve. So identify an axis about which the object rotates. So this is just you mentally checking, okay, the object is rotating here. Then identify the force and determine its distance from that axis, which we'll do in the next example in just a second. Steps 3 and 4 tend to happen in most of these problems. Need to calculate the torque and the moment of inertia. So calculate tau and calculate moment of inertia I. And then use those to figure out whatever the problem is asking for. So I will say that it is very common, it's not a guarantee, but it is very common that you'll be solving for torque and moment of inertia I, and then you're going to use those 2 quantities to then solve for acceleration, or angular acceleration, and perhaps something else after that. So this equation is very commonly used for these bigger problems. So I gave you a brief step-by-step guide on how to work out the problems. So because they are complex, I want us to work out 2 of them together. If you do follow along with this process, you are in good standing. It shows that you have achieved a pretty remarkable thing by, bringing all of these rotational ideas together into one problem. So do your best to follow along, and if you do, congrats, you are really doing well, honestly. These can be challenging. So here is our first problem. It says a 5.9 meter long pole with a mass of 79 kilograms sticks out of the ground 25 degrees from the vertical. Determine the angular acceleration, in other words, alpha. I'll even write that. Alpha equals question mark. That's what we're looking to get as it falls to the ground. So step 1 says to identify the axis of rotation. Well, this object is going to be rotating about the point where it's connected to the ground, right? So this down here is our axis of rotation. We also call that the pivot. So I drew a simplified version of this, or sketched a simplified version of it over on the right here. I exaggerated the angle as well, just so we have some space in our picture to work with. So there's our pole sticking out of the ground, and then step 2 of our problem-solving strategy, if we reference it, we identified the axis, so we were done there. We know it's rotating about the point where it is attached to the ground. So now let's look at the force that's causing it to rotate. Well, the force that is pulling on this pole is its weight, right? It is gravity acting on the object, so it's the weight of the object pulling down on it, causing it to rotate. So the force that is causing this object to rotate is its weight. I'm going to just label it as F. That's the force pulling on the object, but it is its weight. And then it says to also identify the distance from the axis. So how far away from the axis is this force acting? Well, recall our last lecture. In our last lecture, we introduced the concept of center of gravity. This is a uniform object, so the weight of this object should be acting right at the center, right? This is our center of gravity, COG we'll call it. So the force should be acting at the center of gravity, right in the middle. Which means if we want to know how far away this is from the axis of rotation, that's just half of the length. So R is half the length, which is 2.95 meters. Okay, so we know what the distance R is. It's half of 5.9. All we have to really make sure we understand as well is what the angle phi is. We're told that it's the pole is sticking out of the ground 25 degrees from the vertical. Well, this force given by the red arrow is vertical. So this here is our angle phi, the angle between the radial line and your force. So we just did a bunch of things at once. So let's recap before we go forward. The object is being pulled down by weight. Weight acts at the center of gravity, right in the middle of the object. I've labeled that with a red arrow. The distance of that force from the location where this thing is spinning, in other words, the pivot point down at the ground, that distance, because it's at the center of gravity, is half the length of the object. So we're calling it R. And then the angle phi, if you recall our discussion of torque from our last lecture, the angle is the angle between the radial line and the direction of the force, phi. So we are ready to actually solve for the torque. So we just completed step 2 of our problem-solving strategy. Step 3, calculate the torque. Let's do that. We know by definition, torque is given by RF sine phi. We now know all 3 of these values, or well, we sort of do, right? Because in this setup, we have R. Now the force, we're not explicitly given a force here, but we do know that the force is weight. So this is going to be mg, the equation for weight, sine phi. Right? The force is weight. Weight is equal to mg by definition. So with this, we are able to solve for the torque. We have the distance r, which is the 2.95 meters. The mass, which is 79 kilograms. G, which is our acceleration due to gravity, the same 9.8 meters per second squared we've always been using. And then times sine of our angle, 25 degrees. This should give us a torque of roughly 965.2 Newton meters. So we know what the torque is, 965. That was step number 3. Let's move on to step number 4. Calculate the moment of inertia. Well, this is a common shape. This is a rod that is rotating about its end. So we need to use a moment of inertia equation from our common shapes table. This is a rod that is rotating about its end, so we're focused on this object here, a rod rotating about its end, which means we're going to be using this equation. 1/3 m times the length squared. So, moment of inertia is I. I is given by what we just saw in our table, 1/3 ml squared. So we have 1/3 the mass, which was 79 kilograms, times the length squared. The length of the object was the full 5.9 meters, quantity squared. This gives us 916.7 kilogram meters squared, which means we have completed step 4. So we are now ready to solve for the angular acceleration alpha. We have the equation from Newton's second law for rotation that torque is equal to I alpha. So if we wanted to solve for alpha, we simply take torque divided by moment of inertia. I just wrote J on accident. Torque tau over moment of inertia I. So we have both of those numbers. We just calculated them. That's 965.2 Newton meters divided by 916.7 kilogram meters squared. This gives you 1.1 radians per second squared as our answer. Now, if you're wondering where the heck these units come from, it can be tricky. One thing to keep in mind is that a Newton is a kilogram meter per second squared. So a kilogram cancels out this kilogram. A meter times this meter cancels out the meter squared down below. So you're left with per second squared, which is our unit over here on the right. I shouldn't have drawn all that in here. Can I undo? No, of course not. So that leaves behind units of per second squared. And keep in mind, radians are kind of a hidden unit, just like degrees are. You don't really put degrees into your big equations, but they're there. So honestly, to be honest with you, I just memorize the units for angular acceleration. That way I don't have to go through this whole unit analysis every time. Just like regular acceleration is meters per second squared, remember angular acceleration is radians per second squared. Okay, so this is a big problem. It uses multiple different ideas that we've learned throughout these last couple lectures and even back into force and weight and all that. So that's why I said at the beginning, if you can follow along with this and understand it, it's a big achievement and you should be proud of yourself. Because we're applying torque equations, moment of inertia equations, the rotational equivalent of Newton's laws, and so on and so forth. So practice makes perfect, right? So because of that, we're going to do one more example. This is a little bit of a longer lecture because of these big examples, but I think it is important for us to go through a couple of them. So this brings us to example 3. The engine of a small prop plane. So in this case, I'm going to do like a long figure 8. I'm not an artist, but something like that. It's a propeller with a blade on the opposite sides spinning around. So it says that the engine of this plane has a torque of 500 Newton meters. The propeller blade is 2 meters long. It's a single blade passing through the middle and has a mass of 40 kilograms. On startup, how long does it take to reach its final spinning rate of 2,000 RPMs? Okay. Well, in this case, it's sort of a different process that we're going to take because much like we saw in examples that we did 2 lectures ago, we have to first understand that we're given a value in RPMs. Anytime you're seeing that, we need to make sure we know what that value is, and we need to convert it to units that are actually useful to us. So much like we saw in examples 2 lectures ago, RPM, that's revolutions per minute. Per minute is indicating that this is a frequency. It's how often something is happening. So our very first goal here is to take this frequency and convert it. So we are given a frequency of 2,000 revolutions per minute. Revs per minute. Well, we need to convert this. So we know that because, again, we need to convert it because our base unit of time is seconds. This is in minutes. So let's convert this. In every 1 minute, there are 60 seconds. I wrote my minutes up top because we need the original unit of time, or minutes, to cancel out, leaving behind revolutions per second. So this is 2,000 divided by 60, which gives us 33.33 repeating. And that's inverse seconds. We can now use this to calculate the angular velocity. This is a very common process that we've taken in our past lecture. So we can solve for the angular velocity using the equation 2 pi radians times this frequency. So we have 2 pi radians times 33.33. This gives you a value of 209.4. And this is angular speed, so that's radians per second. So this is kind of our preliminary work, right? This is the stuff we're doing at the beginning to get us ready to solve this problem. Well, this is another one of these rotational dynamics problems. We're going to have to apply Newton's second law for rotation somehow. We know torque is equal to I alpha. Right, that's our rotational equivalent equation. So it asks, how long does it take to reach its final speed? That's a time that it's looking for. Well, there's no time in the torque equals I alpha equation. But let's still apply it. Remember our problem-solving strategy. It says that we have to calculate torque and moment of inertia. The good news is torque is already given to us. Right? Torque is given to us in the problem as 500 Newton meters. So this is a torque. So thankfully, we already know that value, which means we just need to calculate then the moment of inertia. We need to solve for I. Well, we don't use the same equation as the last problem, which was 1/3 ml squared, because this is a different shaped object. Let's go back to our common shapes table. We have a blade spinning about a central axis. So what that means is we're going to be using a different equation, because this time we're using this shape, a rod, in this case a blade, spinning around its middle axis. So this time we're going to be applying the equation 1/12 ml squared. So let's do that. We have moment of inertia for a rod spinning about its center as 1/12 ml squared. So we have 1/12 times the mass of this blade, which is given to us in the problem as 40 kilograms. And then the length of this blade, which is 2 meters long, quantity squared, giving us a moment of inertia of 13.3 kilogram meters squared. Okay, well, we now have a moment of inertia and we have a torque. So let's apply our Newton's second law equation, torque equals I alpha. All right, so we can solve for the angular acceleration with this information. So let's go ahead and work that out. So we have torque equals I alpha. So alpha equals torque over, oh, I'm running out of space here, over the moment of inertia. Oh, it's just going to delete it? I don't know why it's disappearing. So it's torque over I. I don't know why that symbol is disappearing occasionally, but that's the idea. So just pretend there's an I there. I don't think it's going to let me keep it for some reason. Yeah, I'm running out of space. This is annoying. Oh. Oh, did I turn on closed captioning? What did I do? Oh, I sure did. 1 second. There we go. Okay, so my goodness, we're having a technical difficulty here. It's just not going to let me do this. There it is. All right, so we have both of these values. The torque was given to us as 500 newtons times a meter, divided by our moment of inertia that we just calculated, which is 13.3 kilogram meters squared. So this gives us 500 over 13.3. This is 37.5. 37.5 radians per second squared. So we have an angular acceleration, but that's not what the problem asks for. It's asking for a time. So this allows us now to actually figure out that time, because we have an equation for the definition of angular acceleration. By definition, angular acceleration is a change in angular speed over a change in time. So we can solve for that change in time, delta t, by taking the equation delta omega over alpha. Your change in angular speed over your angular acceleration. So we have the change in angular speed being 209.4 from above minus 0, because it's starting at rest, divided by the angular acceleration, 37.5. Right, so change in angular velocity, so that's your 209.5 final value minus the initial value 0 over your angular acceleration, and we finally get to an answer of 5.6 seconds. So, challenging problem, no doubt. In fact, I almost needed a second screen to actually work this one out in full. So I just want to emphasize that there are so many things happening here. This one's even bigger than the last. We used torque, we used moment of inertia, we used angular velocity and angular acceleration. We even took the fact that frequency was in the wrong units into the mix. So there's a lot at play here. So this is what I would consider to be sort of the ultimate problem for this material. It combines all of the rotational information we talked about in these past 3 lectures. So to close out our lecture, let's just do one fairly straightforward question to kind of bring things back and move on. So our one question for the end of lecture says the following. 2 solid objects have the same mass. Both are rotating about the same axis. The one that has more of its mass close to the central axis has blank moment of inertia for that axis. Okay. Well, in this one, it's basically just saying that the mass is concentrated more toward the center. So if the mass is closer to the center, what that is showing is that we have a smaller value of r. Well, if you have a smaller value of r in this equation, that means you have a smaller value of I. So the moment of inertia is smaller, because all that mass is concentrated toward the center, giving you a smaller r squared term in the equation, and a smaller moment of inertia as a result. All right, guys. Well, that is it for rotational topics for us. There is a topic of angular momentum. I might get into that in the next lecture, but beyond that, we are ready to move on to momentum, a very important topic. So we're going to get into the impulse momentum theorem, conservation of momentum, and then that will carry us into our discussion of energy and conservation of energy. So we have a lot of really great topics coming up. I can't wait to get to them. As always, I hope you've learned something in this lecture, and I hope that you guys have a great day. Take care.